Recording in progress.
Okay, so welcome everyone to this session of the Gamma seminar. This is a new seminar that we are starting. We want it to be friendly, and we want it so that everyone can collaborate, participate, ask questions, whatever. So the first talk will be by Javier de Lucas from Warsaw on Marsden-Weinstein-Meyer on symplectic geometry. So whenever you want.
Okay, thank you. So as Xavi said, the main aim of these seminars is to present just simple result that can be interesting for all of us, and to boost the collaboration between different groups in Spain and in Poland, and also to encourage students to study topics related to differential geometry and applications in mathematical physics and theoretical physics. So the thing is, as Xavi said, please feel free to ask whatever you want. If you have any question, please do it. Please ask. There is no reason to be ashamed. Okay. Today I will start with something very basic from the very beginning. Yeah. So if you have any question, that don't hesitate. You can stop me at any moment just to make any comment, whatever you want. Okay. I will try to explain the simple things of this theory, and at the same time, from time to time, I will try to give some more advanced comments, but as a commentary. Okay, so the main aim of this talk is to present basic results on symplectic geometry and the Marsden-Weinstein reduction. The talk is divided into two parts. Okay, I will not hurry up. I don't plan to do it. If the talk must be divided into three parts, it will be so. It doesn't matter. Okay. The thing is, those who are not used to this theory, I expect that they will be able to understand the very basics of it. And those who already know a little bit, well, I try to do this so amenable that they will be able to learn something new. So let us start. Okay. So truly speaking, the things I expect to develop during this talk, this series of talks, 1 or 2 or 3, whatever, is symplectic manifolds. I will explain what a symplectic manifold is. Then I will study certain dynamical systems on symplectic manifolds, the so-called Hamiltonian ones. Okay, that they are very important, and they are indeed the basis, for example, for mechanical systems, classical mechanical systems. Okay, and finally, I will explain what the Marsden-Weinstein theorem is. In short, the Marsden-Weinstein theorem is a theorem about simplifying a certain mechanical system in physical terminology, having a certain kind of symmetries which allow us to obtain integrals of motion associated to them in such a way that the Hamiltonian formalism can be reduced. You have a problem with a certain variables in a Hamiltonian formalism, and you have certain symmetries that allow you to reduce the number of variables in such a way that you will obtain a new Hamiltonian formalism, symplectic Hamiltonian formalism. So these are the topics I expect to develop today. So first thing is about symplectic manifolds. So let me tell you that symplectic geometry appear as a consequence of the study of the motion of planets. It was something like, if I don't remember if I properly remember it, toward the 19th century, being the first results given by Hamilton at the beginning and some results about the motion of planets toward the end of the 19th century. It was by, these results were developed by Poisson, by Lagrange, mainly, and other researchers. Indeed, nowadays, everyone has heard the name Poisson or Lagrange. For example, there are the so-called Lagrange points, that they're very important points in celestial mechanics, okay? And when you have a system, for example, with the sun, with the earth, okay? Lagrange points, there are 13 points where you put a certain mass, the mass will be in equilibrium. Normally, there are 5 of them. 1, 2, 3, 4, 5. Okay, there are 5 points. If this is the Earth, okay, so you have these points. And these points were found by Lagrange, and they are very important for several reasons. For example, if you have a satellite orbiting the sun at the Earth, and you want to have it at a point that it has the same relative position with respect to the Earth and the sun, I mean, for example, that they are all turning at the same time, you have to put it on the Lagrange points. So this is a point for Lagrange, for satellites, for example, and for debris, I mean, for asteroids and things of the sort, cosmic garbage, okay, they used to tend to get close to these points, because when there is some motion around the sun, normally when time passes by, it can be proved that the orbits that they are stable are those related with the stable points related to them. And so these Lagrange points give orbits that can be stable in some sense. So normally asteroids and things of the sort, they are used to move in this in these regions. Okay, so here there are a lot of garbage, here there is a lot of garbage, and in this point normally there are satellites. Okay, and this can be for every 3 masses, whatever, one very big, another one very small, another one who is even smaller than the other ones. For example, you can repeat this scheme with the Earth, with the moon, and with the small satellite asteroids which are turning around the Earth and the moon. Okay, indeed, it's fun because these satellites in this system, Earth, Moon, they were discovered, some of them, if I well remember it, by Polish people, Polish researchers, whatever. The thing is that while describing this motion, it turned out that the equations of motion of these planets could be described in a very elegant way by means of a certain geometric and algebraic structures. These were the symplectic manifold and something that is called the Poisson bracket associated to it. So let us say that in a very archaic manner, these structures appear in the works by Lagrange and Poisson. Indeed, they were correcting one each other. I mean, Lagrange found some equations. Poisson said that these equations are not worth it because they can be written in a more elegant way in some way. Lagrange Turner answered saying that yes, but Poisson didn't find a certain important property and whatever. And in this way, the foundations of symplectic geometry appear. Nowadays, the way of describing symplectic geometry is a very, say, elegant way that it seems to be a little bit away from its origins. So the thing is that symplectic manifold is a pair given by a manifold here, and then a differential, a closed differential to form omega. Omega is called the symplectic form, okay? And it turns out that this symplectic form is so-called non-degenerate. What does it mean that it's not degenerate? When you have this symplectic form, these two forms, you can pick up a tangent vector belonging to the tangent manifold at a point x, okay? And what you can do is just pick up the two form, differential two form at a point, which becomes an antisymmetric bilinear mapping, and you can contract with tangent vector. Since this is bilinear, when you fix one term, this is linear with respect to this. And for every tangent vector here in the tangent space to x, okay, you will get a number. So it will be this thing, something that belongs to the cotangent space to the point x. So the thing is, these morphisms can be proved to be linear when restricted to every point x of the manifold n. And if it's invertible at every point x, it turns out that it is said that omega is non-degenerate. This is the definition of a differential two form that it's not degenerate. That this morphism in here, between the tangent and the cotangent manifold, is a diffeomorphism. When you fix a certain point on n, it's invertible, okay? It's linear and invertible. So we can consider an easy example. For example, consider the manifold R2 n, okay? And give certain global coordinates. For example, some canonical ones. You know, you have here two n coordinates. You can say that the first one are called x, the last n ones are called p for some reason. And then you can define the following differential two form, okay? That it is given by the sum for I equal to 1 to n of the xi, the pi, okay? And this two form is closed. It's very easy to check that omega the 2n is equal to 0. This is very simple to say. And moreover, it turns out that it is also non-degenerate, because you can check that at every point, okay, x, if you contract with a certain tangent vector, okay, that will have some coordinates, partial with respect to x. Please let me write instead of partial x, I, yes, write this way for simplicity, okay? And imagine that this tangent vector at x has a coordinate xi. Let me just write the coordinate in this way, because this is the standard way of writing it, okay? And we have the second part. Let me write it in this way, okay? And this is indeed the contraction of a vector field in a certain point with a two form. When you work out this contraction, what you will obtain by making standard calculations is that you will have something of this sort. This will be this x. Okay, so check that this is indeed what we call previously of this, yeah? So this is the image of this tangent vector, is the contraction on the floor with this tangent vector in a certain point, of course, and this is the value. So, and this is a linear mapping with respect to these tangent vectors. And note that if the image of a certain tangent vector must be equal to 0, since these things in here, we are summing over repeated indexes, okay? This is the Einstein convention, sum over repeated indexes. Okay. So the thing is that you can see that if the last part is equal to 0, this means that all these coordinates must be equal to 0. And if this happens, this means that it's equal to 0. And you can see that then the image of the 0 is just 0. And what you obtain is that these morphisms is indeed a diffeomorphism, is invertible, okay? So the thing is that you have seen is that this form is a certain particular example of a symplectic manifold. Indeed, it turns out that for physicists, this is a very well-known two-differential form because it appears in classical mechanics when you have certain coordinates for Hamiltonian system and the associated moment. Indeed, these class of forms allow one to describe the whole classical mechanics Hamilton equations by means of symplectic geometry. Okay, so another thing is that when you have a certain such a differential form, it turns out that some additional structures appear. For example, imagine that you just consider n equal to 1 and you have this symplectic manifold R2 omega 2. Evidently, since you are considering the particular case with n equal to 1, this is a particular case symplectic manifold, but you can see that in this case, the symplectic form is in this way on R2. And this form does not vanish at any point, and it has the rank of the manifold. So it is called a volume form. So it turns out that here, this symplectic form is also a volume form. So somehow one can try to figure out whether when you have a certain symplectic manifold, you will always have a certain volume form. Indeed, for this particular case, for omega 2n, if you make the stereo product of this form with itself n times, it can be proved that what you obtain is a form of this sort. So you see that this form is indeed a volume form. So it turns out that this example you had in here, the symplectic example, has a certain volume form too. So one starts thinking about the fact whether every symplectic manifold has also always a volume form and it is orientable. Yeah, so these are certain things one can start thinking about it. And the thing is that by studying the symplectic manifolds, it turns out that many of the things we have been seeing in this very particular example, they are pretty much extendable to every other symplectic manifold. The first thing you can learn about symplectic geometry is the so-called Darboux theorem. The Darboux theorem tells us that if you have a certain symplectic manifold like this, okay, then around every point of the manifold n, you will always have a certain coordinate system x1, xn, p1, pn, such that the differential form, the symplectic form, will take the form of our previous example. So it turns out that every symplectic manifold looks locally the same, meaning by that every symplectic manifold has coordinates, local coordinates, in which your symplectic form has always the same shape. So that's why it is said that symplectic manifolds, the local properties of symplectic manifolds, are just determined by the dimension of the manifold. Because when you fix the dimension of the manifold, you can have a canonical form for the symplectic form, because you see that here is always the same. The only difference between manifolds is the end. For example, what happens about the dimension of the symplectic manifold? Do you see something interesting? It can be, for example, odd or something like that. No, because as you see, we always say that there's exists coordinates of this sort and they are in pairs. So every symplectic manifold is always even dimensional. There are not all dimensional symplectic manifolds. This is the first thing. The second thing is that when you have omega in this way, if you make the exterior product of omega with itself n times, it turns out as before that you will obtain a volume form. Okay, so the thing is that when you have a symplectic manifold, what you obtain, like in here, is that the symplectic manifold is always orientable. It has always a certain volume form. Okay, so this is the following thing. And now there are more results, because as I told you, locally all symplectic manifolds look the same. They're exactly the same, because the symplectic form can be written always in the same manner for a certain coordinate system. But it happens that globally, it does not need to be so. That means there are certain symplectic manifolds with the same dimension that they are not locally diffeomorphic. I mean, you don't have a certain diffeomorphism between these symplectic manifolds mapping one into the other. Okay, so there are certain cases, for example, torus. Okay, you can see that if you pick up coordinates θ1, θ2 on the torus, okay, which are not global, okay, but can be defined locally. They are not global because there is no way for when you define these angles, okay, it turns out that these functions will not be globally continuous on the torus, because if you start for certain moment for θ1 and you say that this is 0 and you go around the torus, you will become to a point where it will be 2p, and it will be very close to 0. So this, as a function close to this 0, will not be continuous, and there is no way to put this in a better manner. Whatever, it can be proved that even if these coordinates are not defined globally, okay, choosing these coordinates locally on the torus, you can see that the differential of different coordinates will be the same, okay, and they can be defined globally. I mean, for where certain coordinates are defined, you define these things, and defining another coordinate system, you can see that these new coordinates and these can be matched in such a way that where θ1, θ2, θ1 prime, θ2 prime, they will be all of them defined. These both two forms will be the same, yes, in different coordinates. And you see that this form is obviously this form is obviously closed, and it's also non-degenerate. Okay. One can think about the fact whether a symplectic form is defined on a certain manifold. This used to be important because sometimes we have a certain mechanical system in physics, okay, and we would like to know whether we can use a symplectic form to describe it. So in many cases, the first question is whether a symplectic form is defined on the manifold. So, if the manifold is odd dimensional, the answer is no, you cannot. There is no symplectic manifold. Yeah, fuck yourself. There is no way to solve it. This is one thing. The second thing is you have a Möbius strip, which is not orientable, and you would like to make symplectic geometry in it. The answer is no, you cannot, because every symplectic manifold is orientable. So this Möbius strip must be thrown away, and we cannot do anything with it by means of symplectic geometry. But there are more and more and more things. For example, I will explain you some other results that are not so trivial, and they used to be in the literature, and mathematicians love them, and they are sometimes used. For example, take into account that all volume forms are closed. Okay? This is something everyone knows, because on a manifold of dimension n, if you have an n form and you make up the differential of the volume form, you will obtain an n plus 1 form, and n plus 1 differential forms on a manifold dimension n, they are 0. So every volume form, the differential of any volume form is equal to 0. Okay, so you can think of it in the following way. Imagine that n is compact. Okay, so if n is compact, that means that this volume form can be used to integrate, to obtain an integral of the manifold. And since n is compact, this integral will be well defined. Okay, will be a number. Indeed, it's important to see that since the symplectic geometry gives you a volume form, it gives you a way of measuring volumes. Okay, it's a natural way of defining how to measure a volume in a symplectic manifold. Okay, so you have this number. This number is indeed the volume of the manifold M. Remember that volume forms do never vanish. Okay, they can be positive or negative, but you have to think that in these Darboux coordinates, these forces never vanish. They are always positive. So the volume force you have in the Darboux coordinates, they are always positive. Okay, and so this number in here, it would be always positive. Of course, it would be bigger than 0, because you are integrating something, a differential form, which does not vanish at any point. So it must be bigger than 0. But imagine that for some reason, it turns out that this omega n is exact. It's the differential of another differential form. So in such a case, you can apply Stokes' theorem. So you have the infinite is less than that is equal to this thing, because we assume that this volume form is exact. And when you do such a thing, you can integrate over the boundary of the manifold. Normally in here, all the manifolds have no boundaries so far. These symplectic manifolds with a boundary is a separate topic which appears in many applications, and it is interesting by itself. Okay, and there are many research topics related to it. But in general, one assumes that symplectic manifolds have no boundary. Okay, and you come to the fact that the integration of this and something that is empty is equal to 0. So it turns out the integral of your volume form must be equal to 0. But this is nonsense, because we said a while ago that due to the fact that the volume form does not vanish at any point and we are integrated in a compact manifold, it turns out that this integral must be equal to 0. So that means that volume forms from symplectic manifold cannot be exact, because they lead to a contradiction. So it turns out that we are saying that this volume form, okay, there is something. You have a symplectic manifold. The volume form of the symplectic manifold is not exact. So let me recall you that what we are saying is that on a certain manifold n, we have a certain n form that can be written this way. Okay. We know that this is equal to 0, okay, because the dimension of n is to n, to n, yeah, nice, okay. And what you have is that omega n is not closed, because if we're close, we would lead to a contradiction. There is something in a manifold that is called the theorem cohomology. Basically, the theorem space of class 2n on a manifold n is a quotient between closed forms, differential forms on n of rank 2n, module exact forms of rank 2n. Yeah, close it. And this is exact. So when n is symplectic, it turns out that there exists some closed form that it is not exact. So this means that this thing here and this thing here are different. So the cohomology space of rank, of maximal rank 2n on n is different from 0. And you know, these guys are classified for many manifolds. Okay, the cohomology, the RAM cohomology, in general, the RAM, what he did is just to say that these objects, closed form module exact forms, can be related, this space can be related to the topology of the manifold. When you have a 13 manifold, the dimension of this space can be determined by means of the shape of the manifold. And this was the great thing by the RAM, that he was able to tell you the difference between closed and exact forms by taking a look at the topology of the manifold. For example, if you put up 13 torus, okay, yeah, things like this. You see that the torus, the dimension of the torus is 2. Okay? You remember that you have a symplectic form in the θ1, the θ2. As I told you, these are local coordinates, but they can be, it can be defined everything in such a way that this omega, it has sense everywhere. Okay, this is a volume form. Okay, T2 is compact. Okay. And you can see that omega is bigger than the integral over T2 is bigger than 0. Okay. And omega cannot be exact. You know, you can say, okay, omega is θ1 to θ2. And say it is exact, but which is the problem with this one form in here? What do you think? Because a while ago I said that in a manifold like this one, compact like this one, with no boundary, because it has no boundary, the volume form induced by symplectic form cannot be exact. So here it seems that it's so. What is wrong?
Well, it's the definition in coordinates, yes?
Yeah.
So maybe it's not global then.
Yeah, that's the problem. This guy. I mean, this thing is defined globally. This thing, θ1, θ2 are defined locally. But as I told you before, the θ1, the problem is that cannot be defined globally because there will be some point on the torus where it will not be where. Okay, so this is the point. Okay, so let's go on. This now, is everything fine? Do you hear me? Yes, okay. So let's go on.
Maybe could you precisely explain what there is still this echo?
Once again?
Could you precisely explain why for non-compact manifolds this argument does not work?
For non-compact manifolds, yeah, sure. The thing is, this is an interesting question, and the problem with no compact ones is that from the very beginning you cannot do this. It does not exist. It's equal to infinite. Okay, so you cannot apply at the very beginning Stokes theorem for something that it does not exist. Okay.
Okay.
For example, you have R2. I will give you an example, yeah? And on R2, the dimension is 2. You can define omega. It will be dx1, dp1, yeah? This thing in here is what it was called before omega 2. And you can see that omega 2 is indeed exact, globally exact. You see? Yeah.
Yes, I see that.
You could say you could try to apply Stokes theorem to this, and you could say that this will be the R2, and it will be now the x1 dp1, yeah, something of the sort, and this would be empty. So in reality, this would be 0. But the problem is that this is not defined properly. It will be infinite. So you see that Stokes theorem does not work. Okay, well, it does not work. Stokes theorem works, but it works when both sides have sense. If one of the sides has no sense, you cannot compare it, and the relation between this thing and this thing is absolutely different. Both of them, they are not related anymore. This is something a little bit subtle, but well, I mean, it's true. It's one of these things sometimes are written in exams and also questioned in oral exams to check whether someone understood the theorem, I mean, the Stokes theorem, the details, because as I said, it does not work. So I hope that this was clear. And the thing is, in here, when you have the theorem 2, okay, here, it turns out that you can prove that if I remember well, this is equal to 0. That means that every closed form on the plane will be equal to 0. Well, this is due to the fact, this is also basic, that this has a stir-shaped. Okay, and every closed form is exact by the Poincaré lemma. Here, no, T2 is not star-shaped. Okay, but I can tell you that there are many other things. For example, when the manifold N is a Lie group, for instance, is a group with a third time multiplication, it turns out that this thing, the RAM or the K N, can be classified. And there are relations between them. There are Betty numbers, both symmetries, and so on. Essentially, what it happens is that these things, okay, they have a lot of a structure that can be studied. This is what differential topology studies in many cases. So you can have a lot of fun with this. And moreover, these things have application in physics, because sometimes you will have these manifolds and these structures, and you will like to know whether you have a symplectic form, if you haven't, and things like that. And there are topological questions. And as you see, all these topological questions here described are concerned with the topology of the manifold. It means this means that there are not local things, because as I told you at the beginning, locally the torus, R2 and things like that, they are all equivalent when they are symplectic, but when they are globally defined, the symplectic forms, well, as you can see, there are questions that must be also fixed. So the main thing is that whether a manifold is symplectic or not, it depends on certain global questions and certain local. The local one is just about the dimension, that it must be even dimensional. That's everything you need to define locally on a manifold a symplectic form. And when it comes to the globality of this symplectic form, topological problems appear, like here, another one. So it's a matter of interest, something like it interesting, and it's a cool topic to study, very nice. Okay, so the following thing I will explain is that when you have a 13 manifolds, these manifolds usually have a 13 canonical symplectic structure. They are naturally involved with a 13 symplectic structure. Okay, so these examples are so important that they deserve a particular explanation. So that's what I am going to do now. So there is something that for sure everyone knows here, more or less, and this is the cotangent bundle. Yeah, it's just a manifold that is constructed by gluing together the cotangent spaces to every point of a certain manifold. Okay, it's something that is constructed from a manifold. Sometimes this thing in here is called a factor in a certain sense in category theory, because out of a certain thing, a manifold, you can construct a new manifold with certain properties. Okay, but anyway, this was just a curiosity. The thing is that the cotangent bundle is nothing but the sum, a certain sum of cotangent spaces at different points of the manifold. Yeah, this sum is called an disjoint sum. It means that for everything here, for element of every cotangent space, okay, you will construct a new manifold given by a pair of elements. One of these elements will be something of this space that can be one Rn, and another element it will be the point X. This is the meaning of this thing, of this joint sum. It's called normally the disjoint sum because you could sum, for example, the same space for every point X, and even if these spaces would be the same vector space, the disjoint sum would be something different. It couldn't be the sum, the set theory sum of spaces, because if you put here, always imagine that you, to notice the difference, imagine that you do this, and this is the standard sum. This is the same space, just one linear space. Since you are summing all the time the same space, you get the same space, okay? But when you write this, okay, this is a new space, because what are you doing? When you are summing things disjointly, what you are doing is just picking one element of this space E, for example, E, and you are making a pair out of it, given by X and E. And you are adding in the space in a set theory way all these elements, okay? And this is what could be called, for example, a TE, for example. Okay, so this is the meaning of this disjoint sum. Here you have certain vector spaces. And even if these vector spaces could be all the same, as this is a disjoint, for every element of here, you are constructing a pair given by the element in here and the point X, and adding all in a set theoretical way. So what you get in here are pairs of elements. One is a point and another one an element of the tangent, cotangent space to this part. Okay, so it turns out that this thinking here is a set at the beginning. It's a sum of things, but you can introduce a manifold structure on it. And this is done by means of the so-called adapt coordinates. So how this works out? This is very simple. You have your manifold n, and when you have your manifold n, you have your manifold, okay? And for every point, since this is a manifold, you have an open around it that it looks a little bit more like an open set of Rn by means of a certain coordinates x1, xn. The mapping from this open set to these coordinates is called a chart. Okay, so once you have in here this chart, you have to remember that for every point in this open subset U, you will have a certain tangent space to n, okay? The space of equivalent classes of curves passing from them. And you have the dual to it, that this is called the cotangent space. And you can do what is called the cotangent space to U, okay? Well, cotangent space to U. That is the disjoint sum over elements of U of the cotangent spaces of X to the manifold n. Okay, so this is a set, but you can introduce a way of giving 30 coordinates on this set. Okay, how it is done. So for elements of here, you have to recall that it is every element here is a pair of elements. One indexing the point on U, another one on the cotangent space. Yeah. So when you have in here elements in here, remember that these are pairs of elements. One of U, another one belonging to a certain cotangent space. So you can define these coordinates that were defined on n. You can define it on these elements because as these elements are pairs of elements, one of U, one of the cotangent, every one coordinate on here, it can be defined to give you the coordinates of the first part. So I will explain this more in detail in a separate. And so this is n, you have a certain point, you have an open subset, you have a certain chart onto a piece of Rn, yeah, given by coordinates x1, xn, that are here defined on U, and then for every point in here, you will have the cotangent space to this point of the manifold n. And as I told you, you can define a cotangent to U as the disjoint sum for points of view of the cotangent spaces to the manifold n. Okay, and these are pairs of elements given by one point x belonging to U and a certain element of the cotangent space to it. I mean, this is this. Yeah, so the x1, xn are defined on U, are functions of U, but you can extend it to here. Normally, the extension is written in the same way. And how this is done? If you have a certain point x, you only have to do is to define the coordinates on the first part. And you see that this thing will give you n coordinates. And then you can define new coordinates, P1, Pn on here. And how is this done? It's done the following way. Since here you have dx1, dxn, here you have forms, differential forms. So at every point x, these forms form a basis of the cotangent space to N of this. So what you can do is just to write this as a certain linear combination, let us say this way, of this XYP, and these are unique, uniquely defined. Okay, well, this will be in the point X. Yeah. So what you are going to do is just to write lambda 1, lambda n, this point, and this gives you another coordinate. If you put these two things together, you will obtain a map from the cotangent to R to N, and this measures a new chart. Okay, and the thing is that if you pick up another coordinates, you will see that on here, for example, if with this point you get another coordinates defined on U, okay, and this will be C prime, and this will be y1, yn, and you repeat everything, you will notice that due to the fact that here there is a transaction function between U and U with tilde, you will get something in here too. So it turns out that this is a differential, it's a manifold. Okay. So the thing is, on this manifold, you can define as called the tautological differential wave form, the cotangent. And how this is done? This is done by setting certain canonical coordinates in this space and defining this differential form. So you can tell, okay, this is a differential wave form. And how the hell I know that picking up another coordinates, adapted coordinates, this differential form would be exactly the same when both adapted coordinates are defined? Well, the thing is, it can be proved that if you define this on a set of coordinates on another set of coordinates, magically, both differential forms, one form, are exactly the same, but in different coordinate settings. So these things, this theta, the tautological differential wave form, or the Liouville wave form, it is also called the Liouville wave form. It turns out that this differential wave form is globally defined on the world manifold. Yeah. So it's something somehow intrinsic to a cotangent bundle. Once you have a cotangent bundle, you have the Liouville form. Liouville form is that. Okay. So once you have the Liouville form, you can think of, well, I don't like to find this on coordinates. There is some way of characterizing this theta in such a way that I will need no coordinates to define it, and the answer is yes. And this is why it's called tautological. Okay. So imagine that you have a certain differential form on the manifold. Yeah. So a differential form, you already know that is a mapping from N to T star N. This is something everyone knows. Well, a little bit more than that, but for our purposes now, this is enough. So there is some magical thing, and one differential form for every X gives you X and gives you certain beta X. Okay, I mean, this differential form can be written always in this way. Yeah. And you remember that the coordinates in here in this cotangent bundle, they are the point where this differential form is defined, and then these coefficients at every point. So when you have theta, you can see the following thing. When you, this thing, this beta now is something, no, this beta is something that is a wave form in T star N. But at the same time, it can be understood as something that goes from X to the T star N. For every point of X gives you a cotangent vector of this point. So it is a mapping from N to T star N. This is one thing. And at the same time, it's a differential wave form on the cotangent of N. So imagine theta is a one form here. Okay, theta is a one form in here. And it turns out that beta, it can be understood as something like goes from here to here. So since this is a marking, you can make the pull back of theta. And by making the pull back of theta, it will give you one differential form here. But it turns out that you make out the calculations, this is exactly beta, but thought as a differential one form of n. So the theta, the tautological one form, is the only one form that allows you to ensure that the pullback with a certain differential one form of the theta, you will obtain beta. If you try to look for solutions of this equation, you will find that there is just one solution to this thing. So it turns out that you can define the tautological differential one form intrinsically. There is just one. The thing that it turns out to have these coordinates, okay, adapted coordinates is, well, a third time, not to say, not something that it happens, but it can be defined without that. The following thing that is interesting is that when you fix this theta and you make the minus differential of that, you will obtain that in adaptive coordinates, omega is this. But you know, we know this guy already. This is a symplectic form. And since theta is defined globally, omega also. So it turns out that cotangent bundles have symplectic forms defined naturally. And that's why cotangent bundles, sometimes they are, well, is one of the most important examples of symplectic manifolds. In physics, they are very important because normally in physics, you have a manifold n that is basically configuration of a physical system. I mean, the position of something. You have the cotangent bundle, where the p's are the momenta associated with the system you are studying. So when you have coordinates and you have momenta, you will have a symplectic form, a symplectic formalism, and it turns out that Hamiltonian equations and things like can be done in classical mechanics can be described in this way. So it's 22 now. It's a good moment to make a stop. I have introduced the easiest, well, the basic things about symplectic manifolds, the properties they have, and the most important example, one of the most important examples of symplectic manifold in physics. And I will leave the reduction for the second part of my talk. So thank you for listening. It was a pleasure. And if you have any comment, any remark, any question, please go ahead. Thank you. Nothing?
Well, if anyone else does maybe other question, there's echo again.
Mm-hmm.
Well,
wait a second. Javi, could you turn off the microphone of your device?
Wait a second, because here I have a problem with the configuration or something like that. Wait a second, because I don't know what is going on. Because here, if I do this, 1 second.
Sure.
You hear me?
Yes.
Oh, now it's okay? Does it work?
I'm talking. There's echo now. I don't listen.
I mean, do you have any echo?
You have to mute yourself in the tablet or in the computer.
The computer I have switched it off, but before I switched it off and it turned out that it didn't work. I couldn't hear anything, so that's why it's.
Yeah.
But now it's okay.
Try.
Do you have any echo from me?
Yes.
Fine.
No, not from you.
Like we hear ourselves.
Okay, so unfortunately, it's not much better, and it will not be today. I have to look for.
Okay, don't worry. I just was going to ask this deriving with related geometry besides non-trivial compact symplectic manifolds. Well, obviously this is a big research topic, but do you know any other interesting results that having a symplectic factor has on the theorem cohomology manifold?
I mean, there are lots of results of that. The thing is, well, I can give you some references, yeah. The most interesting examples about these sort of things is about Lie groups and things of the sort, yeah, because for some Lie groups, the cohomology groups are from a certain point, sometimes they vanish depending on the time of the Lie group. Then there are the so-called Betty, I think that both dualities, and in Lie groups, I'm not sure if I remember what, I should check it, but for example, when you have a compact manifold, which is a Lie group, and you study differential folds from each, it turns out that the cohomology, the theorem cohomology of the zero and the total space are the same. The first and the n-1 are the same. The second and the n-2 are the same. And there is some kind of this thing of this symmetries. I mean, it's just a game, let us say this way, okay? So there are lots for differential topologies, for differential sorts of manifold. It's an active field of research about looking for these things. There are lots. I can send you some references.
I'm not working on nothing like that. I was just curious.
Yeah, that's out of curiosity. Yeah, me neither. But even in that case, I like it. So I know it. So anything, is there any other question, any other remark, comment, whatever? For the youngest people, because we have several students, I don't know if they want to ask anything. They should feel afraid. I'm not going to evaluate them to put a bad mark today. Any curiosity? Because here they are, I mean, for example, if someone wants to know, this is a very active field of research, and in the Institute for Advanced Studies in Princeton, in the United States, they have plenty of people working on these sort of things. I mean, they are all the time imagining new things about symplectic geometry. But the thing is that well, there are more about, of course, there are certain particular topics related to it. It's not about the general symplectic. For example, there are Floyer homology. There are things about Lagrange, so-called Lagrangian submanifold structure, Lagrangian submanifold. There are symplectic manifolds with boundaries. I don't know what I saw lately. No, I think that they were things of the sort. Let us say that this is a very active field of research and very important. So, any other question? No? If it's about my microphone, I will try to fix it next time. This is a good question. Nothing? Okay, so maybe.
I have no question. I just want to say that very interesting talk. Didn't expect that the beginning. That's for the beginning. All about this. The rank homology and the abstractions. I didn't know about that. It was very interesting.
Let us say this way. It's something that people don't used to say, and but it's there, and it's quite interesting because it's useful. I mean. And the stories that nobody is used to study symplectic geometry, for example, when one studies dynamical systems, the problem is the other way around. I mean, you have a certain vector field and you need a symplectic form that must be compatible in a certain way with the vector field. Yeah. So it turned out that sometimes I try to define a certain symplectic manifold on a certain kind of manifold, and it didn't work out. I mean, I couldn't. I mean, it was, I think, well, again, I should check it, but I think that, for example, in the sphere S4, I think it was S4. I mean, and well, I should check it, but let us say this way. I have a dynamical problem related with quantum mechanics on S4, yeah? And I wanted to study it, well, you know, it was a 4-dimensional manifold. So everyone says, well, it can be a symplectic structure, yeah? And it comes from something that appeared in quantum mechanics. So somehow maybe there is some symplectic form acting on it, okay? Well, the relation with quantum mechanics is a little bit fuzzy, so it's not straightforward, okay? But it appears, let us say it this way. So I was wondering, okay, let us look for a symplectic form. It works. And you know, the typical stuff, you start, you write it locally, everything works fine, because locally everything works fine, because, you know, 4-dimensional manifold, it's even dimensional. So there will be some vector field I have for the dynamical system locally can be rectified. It's a partial with respect to a one variable. So I can put some symplectic form theta coordinates to fix. I try to extend everything, and fuck, 1 point doesn't work. You know, you try to put, okay, 1 point coordinates, well, but they were bad written. Let us put it another way, yeah? Another coordinates, fuck, again, at the same point. It does not work. And once again, at the very end, once check out the cohomology, the biggest cohomology group of the S4 sphere that is compact. Yeah. And it turns out that it's trivial. Every differential for volume form on S4 must be exact, but S4 is compact. So that means that there is no symplectic structure, because if there could be a symplectic structure, you know, Stokes' theorem could lead to a contradiction. So what was this thing telling me? That I had to cut the sphere at a certain point to break the topology of the sphere and put it like it was something open. That was happened. Without a point, the sphere I had without a 13-point line, I don't remember exactly the details, it opens up, it becomes something like an airfoil, and everything works. But if you try to put it all together, it doesn't work, because you would have a theorem, a Stokes theorem, and no, you know, it doesn't work. And it was kind of fun saying, and I think that I remember the paper where I wrote it. And you know, it's useful. I mean, it happens. The dynamical system, as I told you, you put at your vector field, you try to look for the symplectic form, and everything works at the very end. And for a certain time, you say, come on, coordinates, I'm doing this wrong. It must be some, no, there is no way, you know. But topology, yeah, I'm sorry, does not work. Anything else? By that Zoom platform. Okay, maybe. And do you know a way of solving it? You can visit by muting a string in panel at the top of a screen. In panel at the top. Stream. Well, I must recognize that I don't know what it means visit by mutant stream in panel at the top of the screen.
Maybe when you move the mouse at the top, more of the
yeah, I'm doing it, but I don't see. I hear. Oh yeah. I think that, but there is a problem, because it must be something more serious, because it's, well, I mean, do you still? Come on.
You know,
I'm technical problems. I'm taking a look at it, and I mute the stream in the panel, so I don't know what I'm doing wrong. So maybe that it's not that. It must be something else. Well, I will try to check what is going on afterwards. But thank you for the comment. I mean that listeners can mute your screen. Oh, working for me. You try if you want to.
So if we talk, not Hiniko, unmute. Okay, yes, this works.
Yeah, now it works.
Oh, great.
We have to mute you.
Oh, we all have to do it. Okay, great. Now we know.
Okay, so great. You know, we already know how to solve it, but thank you very much, Davian. Very good. Any other question?
Yes, what's next? Next week or?
Yeah,
Yeah,
next Thursday. Same day, same hour, same place.
Okay.
And if someone has some, for me, it can, if someone has any interest on a certain topic, I can prepare it, or if I don't know it. So I'm open to suggestions. Okay. Also, you know, at the very beginning, this is for sharing topics that can be interesting for all of us. So if someone suggests one topic and I can give a talk and think that is interesting, I can do it. I did this because it's one common topic for many of my students. They used to use symplectic reduction for different reasons, and it's also well, many of you know, a very hot topic. Well, for symplectic manifolds, no, but there are other reductions, yeah?
Yeah. Of course, if anyone wants to give a talk someday, just tell us and we'll schedule it.
Yeah.
And if no one does it, we will eventually ask someone to give a talk. Not looking to anyone. Jordi is here. I'm not looking to anyone.
But we are nice. We are not. I mean, you can prepare it very roughly and at your pace. And this is the same. We thought about the seminar as a way of doing this not formally, and also to, in my case, for people to stop being afraid of me. Xavi still remembers certain conferences, yeah?
Yeah,
No one
I
wants
do.
to get close to me.
I do.
And also for the students, if you are working in something and you don't know how to proceed, you can bring it here, maybe a short talk explaining, I'm working in this, I don't know how to follow, and we can discuss between everyone, throw ideas.
This is a very good idea. I mean, it's something interesting. Someone has an idea, wants to learn about, has a problem, well, we can discuss it. Normally, well, it's not, it is about differential geometry. I used to have something to say normally, so I don't, no one knows whether we will find a solution, but well, for sure we will have. Okay, so maybe it's enough for today, I guess, because everyone is tired. Not for Xavi, because he has to send a paper with me.
Yeah.
Yeah.
I'll make myself another coffee, I think.
50 pages long paper.
Yeah, indeed.
And the last pages are crazy. I mean,
Okay, so
we can
thank
finish.
you all for coming and see you all next week.
Yeah, fortunately, you are all invited. If you want to repeat,
Yeah. See you tomorrow, two of you.
See you.
And good night, the people that sleep.
Well, in my case, it will not be a good night because I will finish today again at 2 or 3 or 4. What a week. Okay. Bye.
Bye.
Thank you very much. Bye.
Thank
Bye,
you.
thank you.
Thank you all. You have stopped the. You can stop the recording.
Oh yeah, sure.